Okay, so we've set up now an objective function that incorporates our original constraints by introducing Lagrange multipliers. We want to minimize that function L over W and maximize it over alpha. And you notice that we've written the original objective function now in this new way by multiplying through alpha. So what we do, and this is following exactly the same techniques the last time we saw it, it's just with a more complex optimization problem, is we first minimize over W for a particular setting of these alpha i's. For a particular alpha I, minimize over W and minimize over W naught, and then plug those solutions back into the original objective. So if we want to minimize this thing over W, the vector W, we take its gradient with respect to the vector W. We get that the gradient of this thing is equal to W minus this term here. And now we set that to 0 and solve for W. So we find that for a particular setting of the Lagrange multipliers, alpha 1 through alpha n, the vector W that minimizes this thing for that particular set of Lagrange multipliers is equal to this. Similarly, we take the derivative with respect to W naught. Notice that actually W naught is now eliminated, but we set that to 0, and we get this additional constraint that the sum of alpha I times yi has got to equal 0. Now, if we look at what this is saying, yi is plus 1 or minus 1, depending on which class the ith data point is in. So what we do, and these alpha i's are all positive, so what this is saying is sum up all of the alpha in class 1, and then separately sum up all of the alphas corresponding to the data in class minus 1, and then take the difference of the sum of alpha over class 1 minus the sum of the alphas in class minus 1. That has to be equal to 0. So the sum of the alphas in class 1 has to equal the sum of the alphas corresponding to data in class 0. That's exactly what this is saying. Similarly, if you recall the perceptron and you recall logistic regression, you notice that, again, we're now able to express our vector, our hyperplane defined by the vector W as a sum of the label times the data point times some weight. Remember, for the perceptron, W was equal to a sum over I in some misclassified set of yi xi. We showed how with the soft K and N classifier we introduced a kernel that weights the data points. With the logistic regression, there was a term out in front here that corresponded to the probability of getting it wrong. Here now, these alphas serve as the weights for the SVM, but in a sense, we're still constructing our hyperplane as just a sum of the data points, weighted pre-multiplied by which class they are in, plus 1 or minus 1. The only difference really is going to be how we learn these values for alpha I. Okay, so now we've taken our primal problem, which is minimizing over some parameters. We've constructed the Lagrangian, which takes into consideration the constraints of the primal problem, adds Lagrange multipliers like this. And then we minimized the Lagrangian over the original parameters to get the dual problem. So when we minimize over W and plug back in, we obtain the dual problem, which is equal to this. So if you can verify for yourself that if we take the value, the vector W, and represent it this way, and we plug it back in here for W and here as well, and then if just as important, if we multiply this through against W naught, we have W naught times the sum over I of alpha I, yi. And the constraint that sum has to equal 0 means that we have W naught, whatever the value for W naught is, times 0. So that's where W naught goes in this way. So W and W naught are both eliminated. now we obtain this function. So I've plugged back in for w. I realize that w naught is multiplied by 0. And I reshuffled some terms around. And now I have a function of the Lagrange multipliers only, alpha. So here this term goes like this. And plugging in the value for w here and kind of simplifying this gives me this term here. Subject to the additional constraints now that the sum of alpha I, yi has to equal 0, plus the constraint that these alpha i's all have to be positive or equal to 0. So now I have this dual problem, something that I can maximize over alpha. Maximizing that thing over alpha is still a non-trivial problem. There are many software packages out there that'll do it for you. We're not going to discuss the algorithm for maximizing this thing over alpha. In fact, it's not even obvious that this is any easier or more desirable than minimizing over the primal problem. But we're going to take it at face value with the additional thing to point out here, which will become relevant later, that all that we are required to use in order to solve this dual problem are the dot products between our data points. And so when we see these dot products here, we immediately think that we can now replace that with a kernel. But that's looking ahead a few slides. Okay, so we've run our algorithm and we've found alpha 1 through alpha n. How do we now predict for new data? So remember, what we want is we have a new x naught. We want to predict y naught to be equal to the sign of this function, our linear classifier. That means that we need to find w and w naught. But what we have are alpha 1 through alpha n. So we've actually got everything that we need. Remember when we solved, when we minimized the Lagrangian over w, we found that the optimal w was equal to this function of the data and the Lagrange multipliers alpha. So we've learned alpha, or we've assumed we've learned it with some algorithm, either our own implementation or one of the many good implementations of it. So what we do then is we just simply plug in these alphas and take this sum, and that's how we can get our linear classifier. Or that's how we can find w. For w naught, what we need to do is we need to go back to the Lagrange representation of our problem and notice, what does the optimal solution look like? What is going to happen when we find the optimal alpha 1 through alpha n? So the thing to notice here is that assuming that we found a w that perfectly classifies that our data, that satisfies this specifically this requirement that this function is greater than or equal to 1. Remember, that was our original constraints that we considered. Assuming that we've found that vector w, we know that this term here can either equal 0 or it can be greater than 0. It can't be a negative number. Similarly, this alpha here can be equal to 0 or it has to be greater than 0. It can't be a negative number. So we've found, notice that if this is greater than 0, then any non-zero value for alpha that's positive will make this objective lower. Remember, we want to maximize this thing over alpha. And so if this term here for a particular I is non-zero, if it's positive at the solution, then this alpha I has to equal 0. Right? Similarly, if this alpha I is not equal to 0, if it's positive, that means that this term has to be equal to 0. So these two terms are kind of conflicting with each other. They can't both be positive. If one of them is positive, the other is 0. And that's simply by looking at this objective function and realizing that we're trying to minimize over w and maximize over alpha. That will tell us that at the solution, they can't both be positive. So what that means is that we simply, in order to find the value for w naught, we find a particular I for which alpha is strictly greater than 0. So we've run our algorithm, gotten alpha 1 through alpha n. Some of them, a lot of them will be 0. Some of them will be positive numbers, greater than 0. We pick one of the positive numbers, and then knowing the fact that this product has to equal 0, we can now solve for W naught. Because we have the vector W, we've picked an alpha I that's greater than 0. We can solve for W naught such that this entire term is equal to 0. And what we can show is that no matter what I we pick, such that alpha I is greater than 0, for all I where alpha I is greater than 0, the solution is going to always be the same for W naught. So that's how we can find W naught using the output of our SVM classifier. So let's look at in more detail at how to understand what exactly it is that the dual problem is trying to do. So we've defined the original primal problem. We then switched over to the dual through the Lagrangian representation and said for some reason that working with this dual, maximizing this dual is preferable. Here is where we can see that maximizing this dual is doing something that we originally said that we wanted to do, which is finding 2 points in the respective convex hulls of the two classes that have the minimum distance to each other. So minimizing the distance between the convex hulls. All right, so let's look at the dual problem again. This is what I had written previously. We want to maximize this objective function over alpha 1 to alpha n, such that with the constraints that each alpha has to be greater than or equal to 0. And again, the sum of the alphas in class 1 minus the sum of the alphas for data corresponding to class minus 1 is equal to 0. So remember again, y is plus 1 or minus 1. We sum up all the alpha i's that correspond to data that correspond to an I for class plus 1. That has to equal the sum of all the alpha i's corresponding to data in class 0. So that's what I have here. This constraint simply means that the sum over all data points in class 1 of alpha is equal to the sum over all data in class minus 1 of the corresponding alpha. Now let's call that C. So C is equal to these two sums. We know that it's equal to one number because they have to equal each other. So now if we look at this term here, this is the second term in the objective, we can rewrite this in this way. Notice that what this actually is, this second term, is equal to the magnitude of W squared. Remember we defined this thing to be equal to our vector W that we want to minimize the L2 norm of. So the magnitude of W squared, equivalently, we can write this in this way, where we sum over all the data in class 1, I times xi divided by c, minus the sum over all the data in class minus 1 of alpha j xj divided by c. So the plus here corresponds to the fact that y is going to be plus 1 for these data points. The minus term here corresponds to the fact that y is going to be minus 1 for these data points. And then I do a simple trick of multiplying and dividing by the same thing. So I've divided by c here in both cases. The square term means that I need to multiply by c squared in order to have these two terms cancel out with each other. So this is another way of writing this second term. So I plug that right back in. Notice that the first term here, the sum over all these alphas, is simply equal to 2 times c, where I define c to be the sum of alphas corresponding to one of the classes, because it doesn't matter which class I pick, they're equal to each other. That's 2c. And then minus 1/2 times this term that we just discussed on the previous slide, subject to the constraint that the sum of these two things has to equal constant c. And also that they have to be positive or equal to 0. Again, so this is not necessarily a fully rigorous proof, but if we look at what we're trying to do here, when we maximize over alpha 1 to alpha n, equivalently we're trying to minimize this second term. So we can show that by maximizing this thing over the vector alpha 1 through alpha n. That maximum is also going to minimize this term right here, right? Because this term has to be positive or equal to 0. It can't be negative because of the square right here. And we're subtracting it. And so if we want to maximize something, we can equivalently minimize, or we equivalently are minimizing the negative of something. So when we think through what the primal is trying to do by maximizing over the Lagrange multipliers, alpha 1 through alpha n, we see, or we can think of it as trying to minimize finding the weights alpha 1 through alpha n such that if we construct a probability distribution using those points, we take all the alphas for class 1 and construct a probability distribution by normalizing them. And then we take all of the alphas from class -1 and construct a probability distribution by normalizing them, which is what C is doing. Then we're trying to minimize the distance between 2 points within the respective convex hulls of each of the two classes. Okay, so let's return to the picture now and see if we could find 2 points, 1 point in each of the convex hulls, such that we minimize the distance between the convex hulls. Then what does the direction of the classifier defined by this hyperplane look like? So we've already discussed the geometry of the problem. If we want to find a hyperplane that has this decision boundary, then we know that the classifier, the vector w, has got a point perpendicular. So any vector w, say if this is my w, then this defines a separating hyperplane that's perpendicular to that vector w. Similarly, the vector w that we construct that's going to be perpendicular to this line connecting the two convex hulls has got to be pointing in the direction of that line. In other words, if we have a point v in class 0, -1, say that's v, and this is u in class +1, then the vector that defines this to be the positive region and this to be the negative region, that has this as its hyperplane, the separating hyperplane, has got to be pointing in this direction from v to u. Remember, the arrow says which direction, which side is +1, and then the other direction from the way the arrow is pointing is the side that says -1. And the hyperplane is perpendicular. Therefore, we simply we can construct w by finding the point in the -1 class on the hyperplane. Therefore, we can construct the vector w that defines this hyperplane by taking the point on the convex hull of the -1 class and the point on the convex hull of the +1 class and taking their difference. And so that's exactly, again, if we look at what the vector w is, that's exactly what it's doing. We construct w by taking alpha times y times x and summing over all of the data points. If we just rewrite this in another way, we use our definition of C to be the sum of all the alphas in one of the classes, then equivalently we can write this sum as being the difference between the convex hull and the point on the convex hull in the -1 class and the point on the convex hull of the +1 class. So this point here corresponds to that point, this vector. This vector here corresponds to that point. Their difference corresponds to a vector pointing in the direction from one point to the other point. And then we're simply scaling it by some number c. So that's simply stretching it out or shrinking it.